Swayam Prabha. Digital India. Educated India.
Okay, so where we stopped yesterday, we were looking at the solution for heat transfer, the similarity solution, and this is also called the Pohlhausen similarity solution. Okay, named after Pohlhausen, who continued the velocity boundary layer similarity solution of Blasius, and he extended that to thermal boundary layers, and we saw the derivation of this particular expression subject to these boundary conditions. And of course, you know, from the intuition that for Prandtl number equal to 1, if you replace the temperature variable, non-dimensional temperature theta, with the non-dimensional velocity, the momentum and the temperature equations are identical exactly. So Pohlhausen got the idea that if for Prandtl number equal to 1 they have the same solution, so for other Prandtl numbers there should be some kind of a similarity solution possible. So then he intuitively substituted the same similarity variable which was used for velocity boundary layer, and finally he finds that this falls into the category of similarity solutions. Okay, and of course we have seen by direct integration you can reach to this particular step where this gives you the solution. Of course you need the f from the solution to the velocity similarity, and from there you plug it in and you can numerically integrate it. Or we have also seen the standard way of doing solving all the ODEs will be hereafter by using the shooting technique. So you solve the ODE directly numerically, so that also will give you the same solution for theta, but for all this the solution for f is required. Okay, so you have to solve both of them simultaneously, solve the momentum similarity solution. Once you get the value of f, you substitute into the energy similarity solution, find the solution for theta. So all this also depends upon the Prandtl number, therefore your theta is a function of your location as well as your Prandtl number. So for a given Prandtl number you substitute and you integrate it out and you find a solution. So for different values of Prandtl number you will get different values of theta as a function of eta. So therefore if you plot the similarity solution coming out of this, if I plot 1 minus theta, that is I just convert it as t minus t infinity by t wall minus t infinity as a function of eta, you see for each Prandtl number the slope of the curve changes. Higher the Prandtl number, greater is the slope. So that, which means now you all know that the slope of the temperature profile at the wall directly governs your near wall heat transfer rate. Okay, so we are now going to calculate the heat flux which is carried away from the wall, and we all know that the heat flux is directly related to the slope of the temperature profile at the wall. So greater the slope, greater will be the heat flux carried away, and therefore your heat transfer coefficient which is defined from this also will become higher. So higher the Prandtl number, the higher the heat transfer coefficient. Okay, so now you can probably, once you know the solution, you can convert this in terms of theta and derivative with respect to eta, and then plug in those values. Okay, can you know we have defined theta in this manner, t minus t wall by t infinity. So this can be written as minus k, so dt by dy will be d theta, so t infinity minus t wall into d theta by d eta. I am transforming the variables here into d eta by dy at y equal to 0, or in fact I should apply this condition to d theta by d eta at eta equal to 0. Okay, now I also know my similarity variable eta is y times square root of u infinity by mu x. Okay, so I can just substitute, this should give minus k T infinity minus T wall into what is d eta by dy, square root of u infinity by mu x into d theta by d eta at eta equal to 0. Now d theta by d eta at eta equal to 0. So this is my d theta by d eta. If you integrate this once, you end up with this solution for the slope d theta by d eta. Okay, so you want to evaluate this at eta equal to 0. So we will say that my d theta by d eta at eta equal to 0 should be the value of this f double prime, okay, at eta equal to 0. Okay, so f double prime to the power pr at eta equal to 0 by 0 to infinity f double prime at eta equal to 0 to the power pr d eta, right. Since your f is a function of eta, so the value of slope from that equation will be evaluated exactly at f double prime eta equal to 0. Okay, so I mean when you are doing this numerically, so all you have to do is you have to substitute the value of f double prime from the Blasius solution that you got, right. So you know the value of f double prime at eta equal to 0, so that is nothing but the curvature. Okay, you substitute and then you integrate it. Okay, so then that should give you the value of the temperature profile, temperature slope, slope of the temperature at eta equal to 0. Okay, so when you do this numerically, once you have the complete Blasius solution, it is just a matter of substituting the curvature for in terms of f and then calculating the slope in terms of theta. Okay, so once you do this, you will find out, in fact this was done numerically by Pohlhausen, and he has actually fitted a nice curve. So he gets different sets of values of d theta by d eta for different values of Prandtl number. So depending on the Prandtl number you get different values of this. Okay, so now he fitted a nice curve for different ranges of Prandtl number. For each range, you know, he found a curve fit which is sufficiently good enough to describe it, and this is what Pohlhausen did it. So Pohlhausen's solution was expressed as d theta by d eta at eta equal to 0 for the case where your Prandtl number was extremely small. Okay, so I say Prandtl number approaching 0. Okay, so for such a case he found the curve fit like 0.564 times Prandtl number raised to the power half. This was the best fit which can describe the approximation for extremely low Prandtl numbers. Okay, for moderate Prandtl numbers between 0.6 and less than 15, he found 0.332 into PR power 1 by 3. Okay, and for Prandtl number which is very large, 0.339 PR power 1 by 3. In fact, it's very close. You know, even this could have approximated all the way from Prandtl number 0.6 to infinity. It's only the third decimal point which is just changing. But for very small Prandtl numbers, the functional dependence on Prandtl number itself is different. Okay, so in fact this is a very useful information for us. He has completely covered the entire Prandtl number regimes. Okay, so in fact it's a good exercise. You can, when you are solving this by, for example, shooting method, you will be directly solving for d theta by d eta at eta equal to 0, right. We have seen this, just like the case of Blasius solution where you don't know the curvature, you guess it and try to match the other boundary condition. Okay, f prime of infinity should be equal to 1. The same way here you guess d theta by d eta at eta equal to 0, you guess this and you finally match this solution. Okay, so ultimately when you converge, finally you will directly converge to the correct value of the slope at eta equal to 0. Okay, and if you probably check with the Pohlhausen's correlation, you can get a good idea how good this correlation works. Okay, so you can repeat this for different Prandtl numbers, right? Okay, for different Prandtl numbers you solve this equation, you get the slope, and then you substitute and check whether it satisfies the Pohlhausen's fit. Okay, so that is a good way for you to learn and understand whether this fit is very accurate or not. Okay, so this is what Pohlhausen got. Let us accept it for the time being. So most of the times we are interested in fluids in the kind of intermediate Prandtl numbers. Okay, we are not going into liquid metals or fluids with extremely high viscosity, but with intermediate Prandtl numbers between 0.6 and 15. So we will take that value and then substitute for d theta by d eta for calculating the heat flux. Okay, so therefore my heat flux will become now 0.332 into K times T wall minus T infinity, and just flipping the signs here, into Prandtl number power 1/3 square root of u infinity by nu x. So this is the equation for the wall flux. I want to now go one step forward and calculate what is the heat transfer coefficient. Okay, so my heat transfer coefficient as a function of x will be your wall flux divided by, how do I define it, wall temperature minus reference temperature is my free stream temperature. Okay, so this will be 0.332 K Cr power half square root of u infinity. Now I will non-dimensionalize the heat transfer coefficient in terms of Nusselt number, local Nusselt number, which is defined this way. Okay, so this will be 0.332 Pr power 1/3. So I multiply by x here, so I will be getting square root of u infinity x by nu, right? So which is nothing but the Reynolds number. Okay, where your local Reynolds number is u infinity x by the kinematic viscosity. Okay, so this is the final expression that you probably find in the textbooks. If you have taken a basic heat transfer course, you are straight away given the final expression for flat plate Nusselt number. Okay, so this is how it is coming out. So this is a very straightforward correlation, and probably most of you know by heart, and this is valid for the intermediate Prandtl number range that we are talking about, that is Prandtl number greater than 0.6 and less than 15. Okay, so we can also do one more thing. Rather than being interested in the local variation of heat transfer coefficient and Nusselt number, we can kind of calculate an average value of h for the entire plate. So therefore we can also define an average value h over bar, which is 1 over L 0 to x h dx. Okay, so this is the way I define my average over the entire plate length. Okay, so if I substitute, you can probably do that as a nice exercise. You can substitute and integrate it with respect to x. You will find that the resulting expression will be 0.664 into k Pr power 1/3 square root of u infinity by nu L. Okay, which is exactly twice of h of x, but here x will be equal to L. Okay, so this is exactly twice of the heat transfer coefficient corresponding to x is equal to L. Okay, now same way, if you define an average Nusselt number for the entire plate, okay, depending on the average heat transfer coefficient and based on the length instead of the local coordinate, so you will be getting 0.664 into RE based on the length and Prandtl number 1/3. Okay, so this is exactly twice that of nu at x is equal to L. All right. Okay, so these are some, I think, correlations which are familiar to you, so I am not going to spend too much of time. And so in all these cases, you know that the Prandtl number is a very important parameter, which is the ratio of nu by alpha, so which gives you the ratio of momentum diffusivity by thermal diffusivity. Okay, and you also know from the scaling analysis which we did when we derived the boundary layer equations, the relationship between Prandtl number and delta, we showed that my delta t by delta is approximately Prandtl number to the power -1/2 for one case. For higher Prandtl numbers, this relationship becomes Prandtl number to the power -1/3, but nevertheless you can see that the thermal boundary layer thickness is inversely proportional to the Prandtl number. Okay, so therefore if you are saying that my Prandtl number is much lesser than 1, so your thermal boundary layer thickness is much greater than your momentum boundary layer thickness, and for Prandtl number equal to 1, both are equal and vice versa. Okay, so this is the kind of observation for higher Prandtl numbers. For Prandtl numbers greater than 1, of the order of 1 and greater than 1, you can clearly show that delta t by delta scales as Prandtl number to the power -1/3. Okay, so this is something which was concluded once you calculate your thermal boundary layer thickness from here and the momentum boundary layer thickness from the Blasch's solution. You can simply take the ratio and you find that it exactly scales by this Prandtl number power -1/3. This is something that which you can observe yourself. Okay, for higher Prandtl number. For the low Prandtl number regime, it scales as Prandtl number power -1/2. So in fact you can see here itself. Okay, the slope for the low Prandtl number regime is of the order of PR power half here. For higher Prandtl number, it is PR power 1/3. Okay, so these are some of the observations that you can make. And most of the times if you are looking at oils which are very viscous, you are looking at high Prandtl numbers, or if you are looking at liquid metals, you are looking at very small Prandtl numbers. Most of the practical fluids, air, water and so on, they fall in this intermediate Prandtl number regimes. So that is why we have specially derived the expression for Nusselt number for those majority of the fluids which fall within that Prandtl number range. Okay, so in fact this will be also a very nice exercise which I can give you probably in your homework. You can calculate the thermal boundary layer thickness once you get your Blasch's profile, right. So that is the value of y where your eta corresponding to the eta where your u by u infinity goes to 1 or 0.99, or f prime that you calculate should be approaching 0.99, the corresponding value of y will be delta. The same way thermal boundary layer thickness is defined as the point where your theta goes to 0.99, okay, the corresponding value of y. So you can calculate both, you can take the ratio of that and you can see how it scales. You check the scaling with respect to Prandtl number. Okay, so you can keep doing this for different Prandtl numbers and you will find that it exactly scales in that manner. Alright, so with this we will move on to the next topic, but actually what could have been done, I could have actually started off from the next topic that I am going to talk about now, rather than doing the flat plate solution, because the flat plate solution is a special case of that particular type of flows. Okay, so these type of flows are called as Falkner scan flows. Okay, so let me just give you an introduction to the Falkner scan type of flows before we go into the similarity solution. So any questions so far? on the flat plate is a very basic case, that is why I had to start, so that you can understand how the similarity solution is obtained, how we can solve the ordinary differential equations and so on. The other cases are little bit more not that difficult, but it is just one order of approximation higher, and the flat plate case is going to be a special case of those kind of flows. I did not want to directly start off from there and show you the flat plate. I could have done that to save the time, but nevertheless it would have not been a very good learning experience for you. Okay. Okay. One more thing which I probably will just mention casually before signing off from this. I think all of you have heard about Reynolds analogy. Okay. I think Reynolds analogy is something which is taught in any heat transfer course. So you can also show, I mean, for the case of Prandtl number equal to 1, okay, there is a very good relationship between the Nusselt number and the skin friction coefficient. Okay. So it is expressed in terms of Stanton number is equal to exactly Cf by 2. Okay. So this was called the Reynolds analogy because it was discovered by Osborne Reynolds, and this relationship is very useful because once you know the skin friction coefficient, you can directly calculate the corresponding Nusselt number also. Okay, your Stanton number is another non-dimensional number which is a non-dimensional group which is defined based on your Nusselt number, Reynolds number and Prandtl number. So all these are grouped and just another name is given to that. Now for Prandtl number not equal to 1, people have found that still you can use an analogy. Now that is called as the Reynolds-Colburn analogy because it is an extension of the Reynolds analogy for Prandtl number 1. According to that, your Stanton number into PR power 2 by 3 is exactly equal to Cf by 2. So wherever your Prandtl number is not equal to 1, you can still use the Reynolds-Colburn analogy to calculate the Nusselt number from the skin friction coefficient. So in any way, I mean, already when Pohlhausen did it, he understood the relationship between the Nusselt number and skin friction directly for Prandtl number 1. Okay, for the other Prandtl numbers it was extended based on the Reynolds-Colburn analogy, and therefore these are very useful expressions for flat plate is concerned. You do not have to really be bothered about the heat transfer solution. Once you get the fluid flow solution, you can apply the analogy and calculate the heat transfer solution, especially if we are interested in the heat transfer rate at the wall. Okay, so therefore we are more interested in the Nusselt number and things like that. Okay, so with that I think you can show and derive this yourself. It is not that difficult. I think you can do it. I am not going to spend time, and therefore with this we will move on to the Falkner scan type of flows. Okay, so these are flows with pressure gradient. Okay, so far as you all know, in the flat plate case we have seen that the pressure gradient is neglected and therefore it becomes very simple to solve. Now what happens when you have flows with pressure gradient? Okay, can we derive a closed form analytical solution, or maybe can we find at least a similarity solution which we can solve numerically? Okay, so this was not addressed till the 1930s. So when Falkner and Scan, they studied the similarity solutions derived for flat plate, and they tried to extend that for flows with pressure gradient term also. Okay, so and that is why they have been called as Falkner Scan solutions, at least the flow part. Okay, the heat transfer part was added to the flow part because the heat transfer equation has nothing to do with the pressure gradient. The heat transfer already has been solved. Okay, so once you solve the flow, that F that comes out of the flow goes into the similarity solution for temperature. Okay, so that is going to be much simpler. So the flow is the major complication here. In fact, Falkner and Scan, they discovered that for flows with adverse pressure gradient, they have in fact you can do this from the potential flow theory, that is from the inviscid solution, that you can derive the velocity profile, the free stream velocity, which is a function of x now, it's not a constant anymore, so can be shown to be a relationship with respect to x as cx power m, okay, where c is a constant and m is also a constant, but it is related to what is called the wedge angle, okay. So beta by 2 minus beta, and beta pi is your wedge angle, okay. Now what does it mean by the wedge angle is, if you draw a general kind of a problem with describing this kind of a free stream velocity profile, okay, it will be something like this, okay. So you have a wedge, okay, this is a wedge profile, okay. So you stick this wedge into the free stream, and so initially here your free stream which is approaching will be constant, and now once it encounters this wedge, so there is of course a pressure gradient, okay. So the flow will try to for example here accelerate, okay. So therefore here the local free stream velocity will be a function of x, okay, correct, okay. And this profile is described by this relation cx power m. For this kind of a case, what is the wedge angle? So this is your wedge angle beta pi, okay. So this is a general configuration for which Falkner and Scan has shown the similarity solution, and you can derive special cases of this particular solution, okay. Now you can see if my beta equal to 0, what happens to the wedge? It becomes a flat plate, okay. So these two collapse, and this is just simply flow past a flat plate, and if my beta equal to 0, what is the value of m? M is also 0, right. So therefore my u infinity will be constant, so which becomes basically the flat plate solution. So flat plate solution is a special case of the wedge solutions or the Falkner Scan solutions, okay. Now if my beta equal to 1, for example, how does this flow look, okay. So let me draw the different cases. Beta equal to 0, as you can see that this will be a flat plate, okay. Now if my beta equal to 1, what will happen to m? 1, okay. So therefore my u infinity of x will be cx, okay. Now how does the configuration look? If my beta equal to 1, the wedge angle will be what? Pi. So it will be a vertical plate instead of a horizontal plate, but the flow will be still coming along the horizontal direction. So this will come and impinge, the flow comes like this, it impinges and it goes this way, okay. So this is called a stagnation point solution, because you can see that the flow comes, hits, the velocity has to be 0, so this is a stagnation point, okay. So this is a stagnation solution, stagnation point, okay. So this is, I mean, since it is 2D, this is 2D stagnation flow or stagnation point flow, okay. So these are some special cases of the Falkner scan. Now what happens if my beta is negative? So far I have been discussing the case where beta is 0 and beta is greater than 0. So beta going up to 1. Now what can also, you can also visualize another configuration where beta is negative. Okay, so how could beta be negative? So you can, for example, take this, you can wrap it around inside, it becomes 0 when it touches here, and again you turn it inside, so that becomes negative. And when you do that, if you do completely wrap around this way, you will find this flow cannot flow past this surface, okay, but instead this flow will have to come and then deviate this way, okay. So therefore I am just tilting it upside down. If you tilt it upside down, you can say for beta less than 0, for example, where your m also will be negative, correct. If my beta is less than 0, m also will be negative. So I can have a flow which is something like this, okay. This is my wedge, this is how my wedge becomes, okay. So I take this will be 0, and again I put it this way and make this horizontal, okay. So this will be horizontal, and like this the flow will pass like this, okay. The same thing I am drawing upside down, okay. So the flow will be like this, so what kind of a pressure gradient here it is? Is it favorable pressure gradient or adverse pressure gradient? This is an adverse pressure gradient, okay, because why? Your m is less than 0, so your velocity has to decelerate, correct. So this is an adverse pressure gradient flow. Alright. So whereas the case where your beta is greater than 0, what should happen? The flow should accelerate, your m is positive, okay. So wherever your wedge angles are positive like this, it is an accelerating flow. Where your wedge angle is negative like this, it is a decelerating flow, or it is an adverse pressure gradient flow. In this case it is a favorable pressure gradient flow, okay. So therefore you can see there is a family of solutions that can be derived once you have the basic solution for the free stream. This is coming from the inviscid, this is coming from the potential flow or the inviscid solution, okay. So for this kind of class of problems, there are different configurations that are possible depending on the values of m, which depends on the wedge angle, okay, beta pi. And the limiting cases, some of the limiting cases that we can have a look at is the case of beta equal to 0, which gives you the flat plate solution, beta equal to 1, which gives the stagnation point solution, and negative values of beta, which is an adverse pressure gradient solution. Now if I reduce the value of beta so small, in fact if I make it too negative, what will happen is beyond a certain point the flow will separate, the adverse pressure gradient will be so strong that flow separation will take place. And once the flow separation takes place, the boundary layer theory is not valid anymore, okay. The boundary layer theory is valid only within the boundary layer. Once the flow separates, there is no boundary layer there, okay. Therefore you have to be cautious. There is the there is a lower limit for beta till which you can find solutions, okay. Below that flow separation takes place and you cannot find a similarity solution to those problems, okay. So now what we are going to do is, for these kind of class of problems, we will write down the try to reduce the partial differential equation to a similarity equation. So can you all try to write down the governing equations for this kind of problems? Okay, so for flows with pressure gradient, so how does the boundary layer equations look? Okay, the continuity is still the same. How about the momentum equation? Everything is the same except only one term, which is the pressure gradient term. And we are now neglecting the okay, now when we are not still written the energy equation, first we will take the flow solution and then we will apply that to the energy. Okay, so this is your governing equation. Now we all know how do we calculate the pressure gradient. Okay, I probably mentioned this in the very third or fourth class, okay, when we derived the governing equations for boundary layer. So how do we evaluate the pressure gradient inside the boundary layer? Upstream. So since we have shown that the pressure is invariant of y, okay, so we can evaluate this outside the boundary layer and the same value should be valid inside also. Okay, so therefore if you apply the governing equations outside the boundary layer, so you will get u infinity du infinity by dx. Okay, only your free stream velocity is there, your v velocity is 0, so that should be equal to minus 1 by rho dp by dx, and there are no viscous effects also there. Okay, so you can simply replace your pressure gradient with your equivalent velocity gradients. Therefore this term will become u infinity by dx. All right. So now for the class of problems we are looking at, the wedge flow problems. Okay, this is the form of the velocity profile, c x power m. Okay, so therefore we know the functional dependence of u infinity on x. We can just simply substitute it. Can you tell me how does it look? Since my u infinity is equal to cx power m, my du infinity by dx will be cm x power m minus 1. Okay, so therefore this becomes u du dx plus v du dy is equal to, I can write again u infinity. I can say that this c x power m is again nothing but u infinity. Okay, so I have one u infinity here which I club together as u infinity square, and apart from that I have m and I have x power minus 1. Okay, so I can write this as m by x plus nu. Okay, so this is the form of the momentum equation that I will be working with for the Falkner scan flows. Okay, now what are the boundary conditions? At y equal to 0, u and v will be 0, no slip boundary condition, and y going to infinity, my u approaches my free stream velocity. Now be careful, your free stream velocity is function of x, it is not a constant anymore. Okay, so which is actually of the form cx power m. Okay, so now how do we reduce this to an ODE? The same approach that we did with the Blasius flow. You assume a similarity variable. Let us assume the same similarity variable that we got for the flat plate flows. Okay, because functional dependence of boundary layer thickness on x is going to be the same whether you have a pressure gradient term or not. Therefore your eta, which is a function of y by delta, the functional dependence of delta is still the same. Therefore you can assume the same similarity variable holds good. Okay, only thing here u infinity is a function of x. Okay, so therefore you can write this as y square root of c by nu into, this is x power m, this is minus 1, x power m minus 1 half. Okay, m minus 1 by 2, and also we can define the stream function and show that stream function is related, it is a function of eta, the same way that it was there for the flat plate also. So those things remain unchanged. Where your stream function is defined such that u is equal to d psi by dy, v is equal to minus. Okay, so till now this is nothing new. Okay, this is the same thing we did for the Blasius solution. So all you need to do is substitute for the derivatives now, okay, in terms of the stream function. Now stream function is a function of f, so therefore you can calculate u, v, and you can substitute all of them here. Now only thing is you have this m, and u infinity is a function of x, okay. So once you substitute into this, you will find that I will leave as a nice exercise to you. It will reduce to a ODE in terms of f and eta without any terms from y and x appearing, okay. So therefore this confirms that a similarity solution to this class of problems is possible. Okay. It is not too difficult to show once you plug in all the velocity gradients and your velocities into this expression. Let me call this as number 2. Your stream function already satisfies the continuity, okay. So you have to just plug it in here, and substituting into 2 you get your final ODE, which is free of x and y terms. It is only function of f and eta, okay. So therefore this shows that for this kind of flows similarity solution is perfectly possible, okay, and this is the Faulkner scan similarity solution. So now you can see, now here it is also a function of m, okay. Now if you put m equal to 0, okay, what happens? This term completely vanishes. You have 1 by 2 f d square f by d eta square equal to 0. So this is nothing but the Blasch's solution, okay. So in fact without even touching the Blasch's solution we can straight away we could have started from Faulkner scan and showed Blasch's solution as a limiting case, okay. So all kinds of problems can be approached in this manner. You can put any value of m that you are interested in for that particular configuration and get the similarity profiles for that particular configuration. So this is a function of m right here. So what are the boundary conditions? The same boundary conditions that we have used for Blasch's solution apply here. Eta equal to 0, your f equal to 0. Why your f equal to 0? Which boundary condition does it satisfy? No slip, correct, but exactly which, whether does it correspond to u equal to 0 or v equal to 0? Huh? U equal to 0. What is u in terms of f? What is the relation between u and f? U by u infinity. Therefore f equal to 0, does it correspond to this? So then u equal to 0 should be what? F prime should be 0. So then what does it correspond to? V equal to 0. So go back to the way that we derived the Blasch's solution. Look at the expressions for u and v, okay. So if you put f equal to 0, then only your v becomes 0, because already from the condition that u equal to 0 we know that f prime equal to 0. So for v to be 0, then this has to be 0, okay. And what is the remaining boundary condition? Eta going to infinity, the same thing that we have done for the flat plate, okay. So what is the condition at eta going to infinity? U by u infinity should be 1, or df by d eta or f prime should be equal to 1, okay. So this is called the Faulkner scan similarity solution. So now how do we solve it? Shooting method, okay, exactly the same technique that you did for Blasius solution. Okay, you have a boundary condition for f, you have a boundary condition for f prime, but you don't have a boundary condition for f double prime at eta equal to 0. So you have to guess something and finally match this, satisfy this condition. Okay, you don't worry about, because even if you have this equation, I will just write down, if you apply the shooting method, it will simply reduce to 3 ODEs, which I will just write and stop there, or maybe I can write it here. So the first ODE will be what? F prime equal to G, right? Second ODE will be G prime equal to H. And what is the third ODE? You substitute in terms of F, G and H here, okay? So that will be H prime will be equal to minus, you have m plus 1 by 2 into F into G prime or H, d square F by d eta square H, okay, this has to be F into H plus m into 1 minus df by d eta, the whole, this is yeah, so this has to be f prime square, so this has to be G square, okay. So this is my third ODE. So these are the 3 first order ODEs, okay. All I have to do is march from eta equal to 0 till eta some value of 8 or 10, okay, and the same set of boundary conditions, you know, you guess by Newton's method, successively you reach to the better guess, and then check the condition that at eta equal to large value, some eta equal to 8 or 10, your f prime, which is nothing but your G, should be equal to 1, okay. So that equation has to satisfy. Till then you keep on iterating by Newton's method, you keep guessing better values, and you have to solve the set of ODEs for all the points in the domain, okay. The same, exactly the same technique, all you need to know is the value of m, so which value of which configuration that you are looking, okay. So once you know the configuration, the solution procedure is identical for different, for each configuration you get a class of solutions. So we will stop here. So tomorrow we will complete the heat transfer part of the Faulkner scan solution also.